Hello, now this is a question 15 part A here from Stress and Strain Mechanics 1. We're asked to calculate Young's modulus of elasticity. We're graphing these here and we've load on the vertical axis and extension on the horizontal axis. And we can get the modulus of elasticity E using this formula here. You see this comes from E. Earlier in the notes you can see that E equals sigma over the strain, but you see sigma is force over area and strain is delta L over L. Now the rules then for dividing one fraction by the other is F the first fraction divided by the second fraction, like this, will be the first fraction multiplied by the second fraction flipped over, right? But F over A happens to be F over delta L. You see, then we can swap the delta L with the A, right, and you get F over delta L multiplied by L over A. So this bit here corresponds to the slope on the graph, because the rise is force, right? The force is going up and down, and the change in length, delta L, the run, is going from left to right, the horizontal axis on the graph. So this is the slope of the graph. And L here is the length of the specimen, and A is the cross-sectional area. So we need to get the slope of the graph while it's in this straight line phase here, while it's obeying Hooke's law. So I was messing around with it earlier, and I used these first 2 points here, or the first point and the third point, in order to calculate the slope. So the slope then would be equal to the rise divided by the run, right? And the first point to the third point, the rise there is 40. It goes from 40,000 to 120,000, right? So the rise is 80,000 newtons divided by the run. And the run there, it goes from 0.1 to 0.21. So it goes from 0.1, to 0.31, right? So 0.31, if we take away 0.1 from 0.31, we get 0.21, right? So the run is 0.21, and in meters that's 0.21 by 10 to the minus 3. So we divide that there to get the slope. So we've 80,000 divided by 0.21 by 10 to the minus 3. And that gives us a slope of 380.95 by 10 to the 6. 380.95 by 10 to the 6. Right? And that's going to be newtons per meter there. I won't worry too much about the units. 380.95 by 10 to the 6. So that's going to be this bit here. Right? So we need L and we need A. L is supplied in the question. L is the length of the piece and it's 250 millimeters. So L is 250 by 10 to the minus 3 meters. And the area is the cross-sectional area of the piece. And we're told it is circular and it has a diameter of 25 millimeters. Right? So the area is going to be pi d squared over 4. And that's pi times 25 by 10 to the minus 3 squared over 4. We'll put that into the calculator now. Let's get my calculator to behave itself here. Oh, sure, I'll just put it in there. So that's shift pi and upstairs, and we'll multiply by our diameter, 25 by 10 to the minus 3, close the bracket, square that, downstairs stick in the 4, press equals, and end that, and we get 490.87 by 10 to the minus 6. And that's squared meters. And that is our area, right? So Young's modulus is going to be F over delta L, that's our slope, multiplied by L over A. We've already worked out F over delta L, that's our slope. And what was that again? That was 380.95 by 10 to the 6. So we 380.95 by 10 to the 6 multiplied by L over A, which I'll write them down here a bit neater. 380.95 by 10 to the 6 multiplied by 250 by 10 to the minus 3 over 490 by 0.87 by 10 to the minus 6. And we'll bang them into the calculator. So fraction key there, 380.95 by 10 to the 6 multiplied by 250 by 10 to the minus 3, and all divided by 490.87 by 10 to the minus 6. And I get this, and I'm going to change that. I get 194 by 10 to the 9. 194 by 10 to the 9. That's Young's modulus, so that's going to be newtons per meter squared, I think. And that agrees very closely with the answer supplied there, 197. So I'd be happy enough with that. That was part A.